Okay. Welcome, everybody, to today's meeting of the CUNY Setlist Theory Seminar. We are very pleased to have as our speaker William Chan of Carnegie Mellon University, and he will speak to us about determinacy and partition properties. Okay, William, take it away.
Thank you for having me here today. So this is the first of two talks. So in these talks, in the first talk, I want to review the partition properties and talk about some kind of purely combinatorial consequences of these partition properties. I guess so that'll be most of this talk. So in the next talk, we have to justify some of these combinatorial principles, and we'll do it under AD, which is essentially the only natural known theory where we have these uncountable partition cardinals. But overall, the aim is towards answering this question of Gabriel Goldberg from a few years ago, which I'll state as roughly under AD is the first strong partition cardinal, which happens to be omega 1. Whether the second strong partition cardinal, which happens to be omega sub omega plus 1, can be generated from the first strong partition cardinal by a strong partition measure. So in this talk, it'll be mostly combinatorial. So I won't really even be, using any determinacy arguments or forcing or anything in this particular talk. Okay. So first, let me remind you of the familiar partition relation. So if kappa is an infinite cardinal, and epsilon is less than or equal to kappa, and gamma is strictly less than kappa, then we write kappa arrows kappa epsilon sub gamma to be the assertion that for every partition of kappa the epsilon into gamma many pieces, there is a x subset of kappa with x the size of kappa, so that for every f passing through x, it lands in one particular part of the partition, the edf part of the partition. So for every finite n, omega arrows omega n2, it's just the classical Ramsey theorem. Omega arrows omega sup omega sub 2 is usually called the infinite Ramsey property for holding for all partitions. So this is sort of the smallest example of a strong partition cardinal. And Matthias forcing shows that the Ramsey property is consistent. It holds in the Solvay model, and the same sort of technique can be used to show that using infinity Borel codes that it holds in Wooden's theory AD+. But it is open whether the Ramsey property is true under just AD. And the axiom of determinacy using kind of Martin's coding technique is essentially the only known way to generate uncountable partition cardinals. Okay, but for us, it'll be a little bit more useful to have a slightly different but essentially equivalent form of the partition relation. So first, a little bit of notation. So a function f from epsilon into the ordinal is said to have uniform cofinality omega if and only if there is another function capital F from epsilon cross omega into the ordinal, so that for each alpha, the sequence f alpha n as n ranges over omega gives you a increasing cofinal omega sequence through f of alpha. So we're generally going to be in a context without the axiom of choice. So this is a non-trivial notion. we say that f is discontinuous everywhere if and only if the supremum of f up to any particular alpha is strictly less than f at alpha. And if f is both discontinuous everywhere and has uniform cofinality omega, then we say that f has the correct type. If you have a subset A of kappa, I'll let A to the epsilon sub star denote the collection of increasing functions from epsilon through A of the correct type. So, okay, so this notion of correct type kind of appears very naturally in proofs of partition properties under determinacy. I'll need this concept to make all the statements formally correct, but at the level we're working with, it's not too important if you just think of these as just increasing functions. So using these correct type functions, we get the correct type partition relation, which is a little bit more convenient to use because you have a homogeneous sets which are clubs. So let kappa arrow star kappa sup epsilon sub gamma assert that for every partition of kappa to the epsilon of the correct type into gamma many pieces, there is actually a club subset of kappa and an eta less than gamma, so that every f passing from epsilon into this club C of the correct type, it lands into the eta coordinate part of this partition. You can show that these two partition relations are essentially equivalent. The exponent omega times epsilon ordinary partition relation is equivalent to the epsilon correct type partition relation. If a cardinal kappa satisfies kappa arrow stars kappa sup kappa sub 2, then we'll call the cardinal a strong partition cardinal. And if for every epsilon less than kappa, the exponent epsilon partition relation holds, then we'll call it a weak partition cardinal. So every strong partition cardinal is a weak partition cardinal. And under AD, we have examples of things that are weak partition cardinals, but not strong partition cardinals. With the correct type version of the partition property, it naturally gives us a certain partition filter. So for epsilon less than or equal to kappa, let mu sub kappa sub epsilon be a filter on kappa to the epsilon defined by x belongs to mu kappa to the epsilon if and only if there is a club subset of kappa so that c to the epsilon is completely inside of x. If you have the epsilon exponent partition relation, then you get that mu kappa epsilon is an ultrafilter, which we'll call the the epsilon dimensional partition filter on kappa. And in particular, if you have the strong partition property, then mu kappa kappa will be I'll call it the strong partition measure on kappa. If you have kappa arrows, kappa sup epsilon sub every single gamma less than kappa, just from definition, this implies that mu kappa epsilon is a kappa complete ultrafilter. And a little partition argument actually shows that if you have the epsilon plus epsilon sub 2 partition relation on kappa, this actually implies mu kappa epsilon is a kappa complete ultrafilter. So epsilon less than kappa is kind of important here because apparently it's open whether kappa being a strong partition cardinal alone implies that the strong partition measure is kappa complete. Also, Solovay showed that if the exponent 2 partition relation holds on kappa, then mu kappa 1, which is just the omega club filter on kappa, is a normal ultrafilter. So, assuming sufficient partition properties, these partition measures have a nice property with respect to being a ultrafilter. Okay, so in this talk, I'm not really going to do too much with determinacy, but let me just remind you what the axiom of determinacy says. So fix a subset A of consisting of omega sequences of natural numbers. The game G sub A consists of two players alternatingly picking natural numbers, and jointly after an infinite run, they produce a single sequence X. We say that player one wins the game G sub A if and only if X is in A, and the axiom of determinacy is the assertion that for every A, one of the two players has a winning strategy in the game with the form G sub A. Let me review what we know about partition properties under AD, and maybe in the next talk, I'll say something about how you prove these things. So working under AD, Martin showed that omega 1 is a strong partition cardinal. Martin and Paris showed that omega 2 is a weak partition cardinal, and it's actually not a strong partition cardinal. And then works of Kunin and Jackson generalized this, this pattern for all the projective ordinals. So let delta 1n be the supremum of the delta 1n pre-roll orderings on R. So for us, we just need to know a value of a couple of these. So delta 1,1 is omega 1, delta 1,2 is omega 2, delta 1,3 is omega sub omega plus 1, and delta 1,4 is omega sub omega plus 2. And note that since delta 1,3 is omega sub omega plus 1, this is going to be, this hints at how exactly we're going to try to answer that ultra power question, right? We're going to, ultimately code the ultra power in a sufficiently simple way. Jackson, Kunin for n equals 3 and Jackson in general showed that delta 1 2m plus 1 is a strong partition cardinal, and delta 2m plus 2 are weak partition cardinals, which are not strong partition cardinals. So this continues the pattern for delta 1 1 and delta 1 2. Kecker, Kleinberg, Moskowakis, and Wooden showed that there are actually a lot of strong partition cardinals. So let delta 2 1 be the supremum of the delta 2 1 pre-roll orderings on R. Delta 2 1 happens to be a strong partition cardinal. And in fact, if you take any subset of R, let delta A be the least ordinal delta, so that delta AR is a sigma 1 elementary substructure, LAR. So these are so this is usually called the least sigma 1 stable ordinal of LAR. These ordinal delta A are also strong partition cardinals. So this last statement here actually showed that under AD, if you let theta be the supremum of the ordinals which R surjects onto, there are actually cofinally many strong partition cardinals underneath theta. So there's a lot of strong partition cardinals in AD. When n is finite, the partition measure mu kappa n is essentially a measure on kappa. And Martin showed that if kappa is a strong partition cardinal and mu is any measure at all on kappa, and you somehow know that the ultra power of kappa by this measure is well founded, then in fact the ultra power kappa by this measure is a cardinal. And he also showed that if you took the ultra power by a normal measure, this ultra power actually happens to be a regular cardinal. So applying this result, Martin and Paris showed, okay, so under AD alone, you can actually conclude that the ultra power of omega 1 by the club measure on omega 1 is well founded using this Kunin tree analysis. Okay, I guess originally they probably used indiscernibles. This ultra power is actually omega 2 and is regular since the club measure is a normal measure by that result of Solvay. And more generally, for each n, omega n plus 1 is the ultra power of omega 1 by the n-fold partition measure on omega 1, and the cofinality of omega n is omega 2 for every n greater than or equal to 2. So in particular, the first singular cardinal of AD is actually omega 2 having cofinality omega, no, it's omega 3 having cofinality omega 2. These ultra power representations are actually very useful for combinatorics below the projective ordinal. As an example, the ultra power representation of omega-2 combined with this CUNY tree analysis is essentially how Martin and Parrott showed that omega-2 is a weak partition cardinal. Now, okay, so this handles the finite partition measures, but when you have epsilon strictly bigger than omega-1, mu epsilon are measured on omega-1 to the epsilon, and under AD, these sets are not well orderable, right? So these partition measures are not measures on ordinal, so this result of Martin above doesn't apply. In particular, it will be shown that these ultra powers aren't actually cardinals, and therefore, studying the ultra power of omega-1 by these higher dimensional partition measures are a little bit trickier to study, this will be this will be what we'll be looking at in the next talk, next week's talk. Okay. A familiar result under AD is that, well, actually the consequence of, the perfect set property and the bare property, you can show that there are no uncountable well-orderable subset of R or the power set of omega. As a consequence, omega-1 and R are incompatible cardinals under AD. And this also gives you a kind of choiceless form of the continuum hypothesis, which says that every uncountable cardinal below the power set of omega, the power set of omega is the only uncountable cardinality below the power set of omega. Okay, so then it's natural enough to ask what happens, what can we say about the cardinality below the power set of omega-1 under AD? Okay, so this is there's actually a lot of cardinals below here. I mean, we're far from understanding what the cardinality structure below the power set of omega-1. But at least we can kind of look at some of the important subsets that appear. So, okay, so omega-1 is a strong partition cardinal. So we can ask this question more generally for kappa, which satisfies partition properties. So when kappa is a partition cardinal, these partition spaces give you certain distinguished combinatorial subsets of the power set of kappa. For instance, for each epsilon less than kappa, we can look at kappa to the epsilon. We can also look at kappa to the less than kappa, and at the very top we have the power set of kappa, which is kappa to the kappa. So one question you can ask is, are all three of these have different cardinalities? So under AD, often to get cardinality results, we need to basically understand all potential injection between the relevant sets. So for the purpose of studying the cardinality of these partition spaces, it's useful to understand function from kappa to the epsilon into the ordinal through certain continuity properties that hold almost everywhere with respect to these partition measures. So let me just take a look at one kind of illustrative example. Let phi from omega-1 to the omega into omega-1 be defined by phi of f is just sup of f. And note that under AD or even the partition property, omega-1 is a regular cardinal, so this does make sense. Okay, so what kind of continuity can you expect for this? Certainly, you can't ask this function to be continuous in the sense that it depends on only an initial segment of f, right? So by definition, it's the sup of f. But if you look at it another way, basically this function only depends on one piece of information, just the value at sup of f. So it turns out that this example essentially tells us what the continuity behavior of function from the lower dimensional partition spaces into the ordinals. So let me okay, so let me start with kind of a weak version of this result. So borrowing a term from descriptive set theory, say that define the E0 equivalence relation on kappa to the epsilon by saying that F is E0 related to G if and only if there is an alpha, so that for all beta greater than alpha, F of beta equals G of beta. So they're related if after some point F and G are exactly the same. Say that a function phi is E0 invariant if and only if whenever F and G are E0 related, phi of F is equal to phi of G. So, okay, so we have that if you take an epsilon strictly less than kappa, the cofinality of epsilon is omega. That's going to be important. That's necessary. Assume that the epsilon times epsilon partition relation, exponent partition relation on kappa hold, and fix a function phi from kappa to the epsilon into the ordinal, which is at least E0 invariant almost everywhere with respect to the measure mu kappa epsilon. Then there is a club subset of kappa, so that for any F and G in C to the epsilon, as long as sup F equals sup G, then phi of F is equal to phi of G. So in other words, every E0 invariant function is almost everywhere a function that depends solely on the value of the sup point. So an example of this function is that previous thing we just had here, right? Okay, so this is a weak form of continuity, but only for E0 invariant functions. So if you do, so by doing a few partition argument to, so using that it's cov omega, you can do a few partition arguments to kind of find initial segments of function where the function restricted to that initial segment is E0 invariant. We're able to get a result for more general functions. Again, cov epsilon is omega. Assume the omega time the epsilon times epsilon partition exponent partition relation on kappa hold, and now let phi be any function from kappa to epsilon into the ordinal. Now there is a club C and a delta strictly less than epsilon, so that for any F and G in C to the epsilon, if F and G shared the same delta of initial segment and the same sup, then phi of F is equal to phi of G. Right. So every function in general, you can find every function phi is continuous in the sense that it depends on this fixed initial segment and the sup of the input. In fact, if epsilon is less than omega 1, you can do even better. You can actually show that it's continuous in a finite sense, meaning that there are finitely many ordinals, delta 0 to delta k, so that on some club, if sup of F restricted to delta I is equal to sup of G restricted to delta I, then the value of the functions are the same, right? So when epsilon is less than omega 1, these things are continuous in that it depends only at the sup behavior of finitely many points. Okay, so now how do we use this to get cardinality results? So suppose that kappa is a weak partition cardinal, then for every ordinal chi less than kappa, we have that kappa to the less than kappa does not inject into the class of chi length sequences through the ordinals. And in particular, we have that kappa to the chi has strictly smaller cardinality than kappa to the less than kappa. So let me just sketch in a few words how these short length continuity results are used. So take any function at all from kappa to less than kappa into chi length sequences of ordinals. So we're going to look at the various components of phi. So for each epsilon of cov omega and each gamma less than chi, let phi to the epsilon sub gamma from kappa to the epsilon into kappa, okay, I guess it's actually into the ordinals, be defined by phi epsilon gamma of f. It's just phi of f, the gamma of phi of f at gamma. Now, applying the short length continuity result to these functions, we know that there is an ordinal delta super epsilon sub gamma, which is strictly less than epsilon, which serves as a continuity length for phi epsilon sub gamma, at least almost everywhere. Now, the function that goes from epsilon to delta super epsilon sub gamma, this is a regressive function, right? And since the omega club measure on kappa is normal, using normality several times, you'll find a single delta less than kappa, so that for an omega club of epsilon, this one single delta is this continuity length for phi epsilon sub gamma for every gamma less than chi. So then just pick a sufficiently large epsilon greater than this delta, find any two f and g so that f and g agree up to delta, this common continuity point. They share the same soup, but they're not the same functions. By continuity, because they agree up to that continuity length and have the same soup, we have that phi of f must be phi of g, but f is not equal to g, so this implies that phi is not an injection, right? So what we've shown is that there is no injection from kappa to less than kappa into chi-length sequences of ordinal. Okay. So as a corollary, we have that under AD, all these continuity results and this cardinality result here holds for the familiar weak partition cardinals of AD, including omega 1, omega 2, the projective ordinal delta 1n, delta 2-1, and as well as the stable ordinal delta A. Give me 1 second. My apartment's getting dark. Okay, before I move on, I guess I should say something about the history of this result. So it was known to Wooden that there's this set S1, so that S1 does not inject into omega sequences of ordinals, but he proved this under 80 plus. He used, you need to use infinity Borel codes and then forth over models of forth with the Levy collapse over models of choice for Levy collapses of truly countable ordinals, which are inaccessible in this model of choice. So an important part of his argument is the existence of generics in the actual universe. A Wooden technique is kind of limited to only studying the things below omega 1 because of the need to have generics. Using determinacy arguments, we showed that under 80 plus DC, omega to less than omega 1 cannot inject into omega sequences of ordinal, but the techniques we used were very specific to omega 1. We didn't even know how to prove it for delta 1,3, and even worse, these techniques definitely don't work for these limit cardinals, which are strong partition cardinals like delta 2,1 or delta A. So even though, like, for instance, delta 2, we know a lot about delta 2,1 under AD, it has all sorts of reflection properties. The only argument we know to establish like this above continuity result for delta 1,2 passes through this kind of purely combinatorial argument. Okay. Before we move on, let me just give you one example to show you that in all our results, the assumption that epsilon has cov omega is usually necessary. You can show that the ultra power of omega 2 by the club measure on omega 1 is omega 3. So using this fact, we can define a function psi from omega 2 to omega 1 into omega 3 by letting psi of f be the image of f under this ultra power map. So certainly this thing is not going to satisfy any kind of continuity result like we were looking at, simply because it's like an ultra power type map. But note that in this example, we have psi mapping into omega 3. if you actually restrict the functions from omega to the epsilon into omega 2, where epsilon, of course, is less than omega 2, you actually are able to prove these continuity results for every single epsilon, even if it has cofinality omega. So let me just summarize that here. So for functions from omega to the epsilon into omega 2, you get this short length continuity where it depends on a fixed initial segment and the soup. And you even get this even stronger form where it depends on only the soup behavior at finitely many points. And this is kind of unique to omega 2 under AD, and it's made possible by the fact that omega 2 it has ultra power representation as the ultra power of omega 1 by the club measure on omega 1. Okay. So, so far we've been talking about functions that go from the lower dimensional partition spaces into the ordinal. Now the next thing we want to do is talk about these functions from the strong partition cardinal back on the strong partition space back into the strong partition cardinal. So it turns out that there's actually a sort of a club uniformization principle that's very useful for combinatorics on strong partition cardinals. So essentially, these uniformization principle gives you the ability to select a homogeneous set out of a family of clubs which are indexed by bounded sequences. So the first type of result we have is, I guess I call it the everywhere short length club uniformization at omega 1. So the hypothesis is assume AD hold and the principle of uniformization hold. This says that every relation on R can be uniformized. Then every relation R on omega 1 to the less than omega 1 cross club subset of omega 1, which is subset downward closed in the club coordinate, meaning that if RL D holds and C is a subclub of D, then RL C holds. Then you can find this function gamma, which lambda, which is defined on all of the domain of R, picking out clubs, so that for any L in the domain of R, RL gamma L holds. So in other words, gamma L is a club which is associated to L with respect to this relation R. So the argument here uses, it's kind of specific to the length of the indexing family. So the best we can do in this direction, this kind of everywhere direction, is everywhere countable length club uniformization. So assuming AD and all sets of reals are Suslin, all sets of reals have certain tree representations, let gamma be a point class which is closed under and or for all R and has the scale property. Let kappa be what's called the pre-well ordering ordinal of gamma. So this is the soup of the length of the pre-well orderings on R, which belong to the delta point class associated to gamma. Then for every relation R on kappa to the less than omega 1 cross club subset of kappa, which is subset downward closed in the club coordinate, you have a uniformization function which works on all of the domain of R. But let me just point out that these everywhere club uniformization results, just like how uniformization is not provable under AD, these generally cannot be, these are not, this principle can't be proved under AD alone. But for our purposes, so for us, we're studying combinatorics almost everywhere with respect to partition measures. So we don't really need to be able to do, we don't need to be able to uniformize everywhere. Usually for us, it's good enough to be able to uniformize almost everywhere. And we can prove versions of this under AD. So let me just make a definition. So say that almost everywhere short length club uniformization at kappa holds, if and only if, for every relation on kappa to the less than kappa cross club subset of kappa, there is a club C and a function lambda defined on the domain of R intersect C to the less than kappa, so that whenever L is in the domain of R and also in C to the less than kappa, lambda of L will be a club that is associated to L with respect to this relation R. So with Jackson, we showed that almost everywhere club uniformization at omega 1 holds. So as usual, everything at the first proof of everything at omega 1 is always a little bit misleading, or it doesn't really generalize. So what we do here is that we use the Moshkovakis coding lemma to somehow find a relation, a projective relation on R, which codes the original relation R, at least almost everywhere. Projective relation can be uniformized under AD, so we pick a uniformization for this thing, and then using some the well-ordered additivity of the meager ideal, you do certain generic coding arguments that allow you to find this uniformization. Again, these generic coding arguments and category arguments don't really work very well when you're beyond omega 1. So for some time we didn't know how to even prove this for delta 1,3. But later I showed that actually this club uniformization principle do hold at the familiar strong partition cardinals of AD. They hold at omega 1, the projective ordinal, delta 2,1, the stable ordinals. So I'll next time I'll say a little bit more about how you prove this, but kind of the method that we use to prove this is sort of important for the ultra power question. So to prove this result, you need to come up with this improvement of Martin's good coding system idea that allows that incorporates in coding for the bounded sequences, the bounded length sequences of a strong partition cardinal. This is a little trickier than it sounds because Martin's good coding system has very restrictive definability criterions, right? So it's a little tricky to kind of merge these ideas together. But it'll turn out that this coding family kind of gives us the necessary coding mechanism to code the ultra power in a sufficiently simple way. So I'll say more about this next week. When kappa satisfies this club uniformization principle, and kappa itself is also a strong partition cardinal, in every instance I know they always come together. You actually have a stronger form of this club uniformization. There's actually a single club C, so that for every L which is in the domain of R and also in C to less than kappa, the club above the sup of L is actually a club which is associated to L with respect to the relation R, right? So it's actually one single club that so that if you chop off an initial segment, it will work. So these are the club uniformization principles, and the primary application of these things are to get continuity results. So assume that kappa is a strong partition cardinal and this club uniformization principle holds at kappa, then for every function from kappa to the kappa into kappa, there is a club C that should be a subset of kappa, so that for all f in C to the kappa, there is a delta less than, that should be kappa again, so that for any other G passing through C to the kappa, if F up to delta is equal to G up to delta, then phi of F is equal to phi of G. So note that this is kind of the natural familiar notion of continuity given from topology, right? I guess if you put the discrete topology on kappa and you put the topology on kappa to the kappa generated by bases that extend bounded sequences, and this is the almost version of continuity with respect to that topology. So let me just say something about how club uniformization is used to prove this. So the trickiest part of this argument is basically to show that a partition is homogeneous for the side we want it to be homogeneous for. So define a partition P on kappa to the kappa by P of F, let's say it's on the 0 side, if and only if there is a delta less than kappa, so that for every single club D, there is some G passing through D, so that phi of F restricted to delta with G following afterward is less than G of 0. So this is a little bit more natural than it seems. So using the strong partition property, there is supposed to be a homogeneous club C0 for this partition. So I want it to be homogeneous for the 0 side. So suppose it didn't happen to be homogeneous for the wrong side. Define a relation on C0 to less than kappa cross club by just saying that RL of D hold if and only if for every single G passing through D, phi of L followed by G is bigger than or equal to G of 0, right? And since C0 is homogeneous for P for the one side, by taking negation, you can check that this implies that the domain of R is actually C0 to C0 to less than kappa. Now, apply the club uniformization to this relation R. So this gives us a club C1, so that for any L in C1 to less than kappa, the club C1 above the sup of L is a club which is associated to L with respect to this relation R. Now pick any sequence F passing through C1. For any alpha, we know that C1 above the sup of F restricted to alpha is a club which works for F restricted to alpha. And also the tail of F after alpha is a infinite sequence that passes through C1 above the sup of F restricted to alpha. So by definition of R, we have that phi of F, which you can decompose that phi of F. Oh, that should be restricted to alpha. Phi of F restricted alpha followed by the tail of F after alpha has to be greater than or equal to F of alpha. Now, so alpha was arbitrary, right? So what we showed is that phi of F is bigger than or equal to F of alpha for all alpha. And since F is a strictly increasing function, this implies that phi of F is not an ordinal in kappa, but that's impossible, right? Phi is supposed to be a function mapping into kappa. Right, so because of this contradiction, we've shown that C0 has to be homogeneous for the 0 side. Okay, so as I mentioned, this is kind of the trickiest part of the argument, and now it's fairly easy to see how to get continuity. So C0 is homogeneous for the 0 side. So let K be the collection of bounded sequence L, so that for every single club D, there happens to be a G passing through D, so that phi of L followed by G is less than G of 0. Since C0 is homogeneous for P on the 0 side, what this gives us is that every single function F passing through C0 to the kappa has an initial segment in K. So in some sense, this set K is kind of dense. It'll turn out that the points in K will be the continuity points of phi relative to the club C0. So what is the constant value then? So for each L in K, define phi of L to be phi of L of G is phi of L followed by G. So just the function after L. Using the fact that L is in D, if you do a little partition argument, you can show that there is a subclub D, so that for every G in D, phi L of G is less than G of 0. And using kappa completeness and some partition argument, it's kind of like a normality argument here. You can actually find a even smaller club E and some ordinal C sub L, so that for every function passing through E, phi L of G is constantly C sub L. And this ordinal C sub L is going to be the constant value associated to this continuity point L in K. So to be a little precise, define psi from C0 to the kappa by psi of F is C sub F restricted to delta F, where delta F is the least delta, so that F restricted to delta belongs to K. So remember, we showed that C0 has the property that every F has an initial segment in K. So by the way I've defined it, this is clearly continuous. And if you do a few more partition arguments, you can actually find a subclub C2 so that phi restricted to C2 is equal to psi restricted to C2. And since we know psi is continuous, we have shown that phi is continuous almost everywhere. Okay. Okay. So this completes the proof of continuity. But for the ultra power question, continuity alone is actually not good enough. Just because something is continuous, it's still kind of very difficult to tell whether a bounded sequence is a continuity point. It kind of requires quantifying over all possible extensions, and we'll see next time that that's too much for us to do. But you can actually prove a finer continuity property that will allow us to recognize continuity points in a sufficiently simple way. Under the same setting, if you have a function f, let beta f be the least beta so that phi of f is less than f of beta. So you can find some club C so that for every f passing through C to the kappa, f restricted to beta f is actually a minimal continuity point for phi relative to C. And using this, we have as a consequence that for any bounded sequence L in C to less than kappa, if you are able to find any G passing through C to the kappa so that phi L followed by G is less than or equal to the sup of this bounded sequence L, then we will know for sure that L is a continuity point for phi, at least relative to this club. So this last part here is what we're going to actually use to next time to determine relatively easily that something is a continuity point. Let me give you one more cardinality consequence of continuity. So if kappa is a strong partition cardinal satisfying the club uniformization principle, then the cardinality of kappa to the less than kappa is strictly less than kappa to the kappa, which is of course the same as the cardinality of power set of kappa. If you had an injection of kappa to kappa into kappa less than kappa, you would look at like the length function and apply continuity to something to that function. Let me just point out that this is actually not the most efficient way to prove this result. You can actually prove it from the strong partition property itself. There's also certain kind of arguments using constructibility to prove this kind of argument as well. Let me see. Oh, okay. Okay, so now we have a continuity result, a couple continuity results for functions on strong partition spaces. So naturally, you can ask, what is like the best kind of continuity result you can get for functions from omega1 to omega into omega1? Is there any type of finite continuity result that you get for these sort of things? So a plausible candidate for a finite continuity property would be something like, does there exist finitely many functions, gamma 0 to gamma n-1, so that for all f and g in a suitable club, if sup of f restricted to gamma I of f is equal to sup of g up to gamma I of f, right? That is f, that's not a typo. Then is phi of f equals to phi of g? In other words, are there finitely many functions that tell you the finitely many places that the function phi will depend on? So unfortunately, this is just not true. And this example kind of tells us where the problem happens. Given a function f from omega1 to omega1, call an ordinal alpha a closure point of f if and only if sup of f restricted to alpha is alpha. The collection of closure points will be called C sub f, and this actually happens to be a club subset of omega1. Define phi of f to be the minimal closure point of f. And so you can check that this function here will never have a finite collection of functions lambda 0 to lambda n-1 satisfying the property I mentioned, the candidate for the continuity property I mentioned above. But this function is defined using these closure points, and it turns out that closure points are basically the only way that you can code infinite information into a function from omega 1 to omega 1. So this is made precise by the following result. Okay, so assume dependent choice, omega 1 is a strong partition cardinal, and let's say the club uniformization principle holds at omega 1. Fix a function from omega 1 to omega 1 into omega 1. Then you can find a club subset of omega 1 and finitely many functions, lambda 0 to lambda n minus 1, so that for any f and g passing through this club, okay, so the new condition is that the closure point of f has to be equal to the closure point of g. So they share the exact same closure point. And suppose that the supremum of g up to lambda I of f is equal to the supremum of f up to lambda I of f for every single I less than n, then phi of f is equal to phi of g, right? So as soon as you add in that they must share the same closure point, then you get kind of this analog of this finite continuity property. Okay, so using some argument with Moshko-Baket's coding lemma, this result does hold in AD, even though AD doesn't satisfy DC, right? Okay, I think, okay, so I just have one more result that we might need for next week's talk. Assuming kappa is a strong partition cardinal and the club uniformization principle holds that kappa, we have the existence of this following inner model. So for every x and r, there is an inner model containing x in which kappa is a measurable cardinal, but it is also a limit of a discontinuous sequence of measurable cardinals. So, I mean, we'll be working under AD, so I guess, you know, there are numerous different consistency results you can look at to get this sort of result. But this is true purely from combinatorial principles. And, you know, I was kind of thinking about it. I wonder what is the easiest way under AD to get this result. But anyway, so I can at least tell you what the model is. Given an f in kappa to the kappa, so you can break an omega 1 sequence into omega 1 many blocks, omega 1 many omega blocks. So let f sub alpha from omega into omega 1 be the alpha of omega block of f. Let c sub f of alpha be the tail equivalent class of f sub alpha, or whatever we call the E0 class from before. And let bar c sub f be the sequence of all the associated tail classes. Let nu sub f be the tail filter on the sup of f sub alpha. And let mu be the omega club filter on kappa. So using the club uniformization, you can show that for at least mu kappa kappa almost all f, hard as computed in Lx mu of mu f, using parameters x, mu, and the sequence c bar of f, mu intersect hard of blah, blah, is a normal measure on kappa. And for each alpha less than kappa, the tail measure nu f sub alpha intersect hard of blah, blah, blah is a normal measure on the sup of f alpha, right? And so this will be a model satisfying the theorem. These type of results are, I guess, what we call like kind of the investigation of the stable theory of f for almost all f in some partition measure. So let me just end with some results along these lines that you prove using club uniformization. So assume kappa is a strong partition cardinal satisfying the club uniformization principle. Then for mu kappa kappa almost all f, L of f is a model satisfying GCH, sigma 1 determinacy, the failure of delta 1 2 determinacy for each alpha less than kappa L of f thinks f of alpha is a strongly inaccessible cardinal, and L of f thinks that there are no measurable cardinals. These type of results are follow from showing something like showing the existence of certain inner models. You can show that for almost all f, L of f has a sequence of normal measures, mu bar sub f, with with an associated discontinuous sequence of critical points, so that L of f is a certain generalized Prickly extension of L of mu bar of f. This kind of Prickly forcing is it's the type of Prickly forcing that Fuchs was studying in his thesis. Once you know that L of f is a forcing extension of these sort of kind of canonical models with measures, you can use kind of forcing techniques and Kunin's iteration type of argument to establish some of these claims in the above theorem. How am I doing on time? Okay. Yes. So this is all I have for today. I think I got through most of the combinatorial consequences of partition properties that I'll need to use for next talk. So in the next talk, I will be looking at the ultra power of this question of Goldberg concerning this ultra power of omega-1 by its strong partition measure. And there, I really will need to tell you something about determinacy and how to code things using determinacy. Anyway, thanks for listening. I hope you come back next week.
Really good introduction and overview.
Sorry, I couldn't hear anything.
Sorry, I didn't have my mic down. Sorry about that. Yeah, no, I just was thanking you for a very nice talk. Very good overview. Are there any questions?
I was wondering if, in general, you would expect that for all cardinals kappa less than theta under AD, kappa to the kappa doesn't inject into ord to the less than kappa, or is it possible that that fails at cardinals that aren't weak partition cardinals?
No, as far as I know, it could. Yeah, I think no. Yeah, I don't know of any counterexample, and I think it probably should be true. But yeah, as soon as you get up to like omega-2 and omega-3, so yeah, like omega-3 is not any partition property at all, right? I don't really know how to prove these things, and there's some very weird combinatorial properties of omega-2 that we don't know how to resolve.
What are you referring to for omega-2?
Like there's something like yeah, can you split omega-2 to the omega-2 into, yeah, if you split omega-2 into omega-2 to the omega-2 into two pieces, is at least one of them size omega-2 to the omega-2? Yeah, I don't think, yeah, without this strong partition property on omega-2, yeah, so like funny things like this that don't know.
Let's see. Maybe, could I ask a quasi-historical question? So as far as I remember, some of the very early work on consequences of strong partition properties was done by Gene Kleinberg. Is there, I think he had some things about after a strong partition cardinal that you get a few row bottom cardinals and then a Janssen cardinal, things of that sort. Does that connect with what you're doing other than just it uses strong partition properties?
Yeah, so I mentioned like so I think Kleinberg, so without AD, as long as you know that ultra power is well founded, I guess he called these things kappa 2, kappa 3, and so on. Right?
Yeah.
Yeah, so he established without AD that these kind of ultra power thing share some of the properties that omega 2, omega 3, omega 4, and so on have. But I think he, at least in his book, he only took ultra powered by the finite partition measures, right? So those are essentially measures on ordinals. So I guess in the next talk, I'll be doing these ultra powered higher than omega, right? And they're not measured anymore. And I don't think Kleinberg book, I think Kleinberg book only went up to the finite partition measure.
I think that's right, yeah.
Okay, well, sounds like everybody is satisfied. I'm looking forward to the second part next week. Thanks again for the great talk. And yeah, have a good weekend, everybody.
Hi, everybody. Thank you. Great talk.
Thank you.